Now I would like to introduce our speakers. We have Jonathan Allen, who has been here before and has talked a great deal from Dogani. Jonathan is a coastal hazard expert.
Coastal geomorphologist.
You say that.
Did everybody get that?
Can you spell that?
Coastal geomorphologist.
Perfect. Thank you.
I study the beach.
And Laura Gable is the coastal hazard specialist.
Sure.
Sure.
Yeah, geologist.
Geologist. And so what they've done is put together a really good program that talks about the literal time it'll take you to get from here to there. They've rolled it out in Rockaway, Cannon Beach, a number of other places. They're starting here, and part of what draws them here is the Nehalem Bay State Park. That's such a critical component. So I'm going to turn the program over to you.
Thank you, Linda.
Sure. So on that note, let me ask you this.
Bio. I'm so sorry you asked
So we're in the inundation zone here. So does everyone in this room know where they would need to go in the event of an earthquake? Where do we go? Fantastic. You guys pass? We're done? We're good. No, and so that's really important. That's why we're all here, and that's why we do a lot of this sort of work in communities up and down the coast is really trying to reinforce that knowledge, because reality is it's going to happen at some point in time, and every person needs to know where the nearest point of safety is in their community, but even as you travel up and down the coast. And so one of our goals has been over the last several years, now that we've actually completed a lot of the work for developing evacuation maps and having a really thoroughly sound understanding of the risk along our coastline, is that we provide that information for that entire coast now. And so, every person can conceivably locate themselves now anywhere along the coast and figure out where high ground is. There are many different tools available, be it static evacuation type brochures that you can pick up in the various emergency facilities, fire stations, emergency managers with those groups. You can also download an app now that actually allows you to locate yourself anywhere on the Oregon and Washington coast, and it'll tell you whether you're in the zone or not. And so all that information is critically important. What we're going to talk about here today is work that we have been doing now for almost 4 years. Starting back in around 2014, 15, actually 2013 was up in Cannon Beach initially as a pilot effort, which was to really try to figure out explicitly, quantitatively, where people need to go to reach safety at literally the house level. And based around that, because we know the time at which it takes for the wave to come in and roll across the landscape, we can actually figure out how long it's going to take you to get to high ground, but then also how fast you need to be traveling. And so we've been applying this approach, and Laura's going to be talking a lot more about this in her presentation. We've been rolling this approach out now in multiple communities. I think we're, by the end of this year, we should have somewhere around 16, 17 communities mapped with this sort of very detailed quantitative evacuation modeling having been completed. So we started in Cannon Beach, we rolled it out to Seaside, we've done most of Tillamook County, we've been working down in Lincoln County, and in the last sort of year or so, working with Tom Bender, who's in this group here, we recognize the importance of places like Nehalem State Park. I mean, it has the capacity there of as many as 2,500 to 3,000 people who are visitors in this area, who unfortunately probably are not as well trained and knowledgeable as you all are of the tsunami risk. And that poses a major challenge both for the park, but for the Nehalem EBC who are planning for this, and you all as well. And so again, one of these sort of goals is to really try to provide them with good information that they can use to, again, figure out where the best places are to evacuate to, and how much time they've got, and then obviously begin to pass that information on to the public at large. So that's a really key part of the work we are doing now. I'm going to turn it over to Laura, and she'll explain in a lot more detail the process.
Yeah, so it is really detailed what we're doing, and Linda said what we were doing is more accurate than actually walking these routes. I would say that it's a sister product. You know, actually how it feels on the ground is really valuable and is just as valuable as what I'm showing you, because this is really a computer exercise, and it's meant to sort of illuminate important spots in the community, important routes, important pieces of infrastructure, bridges and such. And so not only is it also helping, like John was talking about, with, our vulnerable visitor community that come to these state parks and they come to our towns for the weekend. But it's also looking at the complicated geography and other things that might be roadblocks to making evacuation as simple as possible for everybody. And so we like to use this picture from Japan showing the wave inundating across the Sendai Plain and crossing a river where there are several bridges that cross that river. And we feel that this is a really similar situation to Seaside, where we have a large population that's west of these two, the Neawana Creek and Nicanacum River, and they have to decide which way to go, east across those bodies of water or south towards Tillamook Head, and which of those bridges will likely be standing after the earthquake and be available for evacuation. It's those kind of questions that we're asking with this work, and just trying to provide that information then to emergency managers and planners and that sort of thing to help inform all the work that people are doing to help prepare. So, okay, I've already started talking about this. We know this is an event that's going to happen on our coastline, and we generally know what it's going to look like because we watched it happen in Japan in 2011. And so we understand that prompt evacuation is very important, and the Japanese know to evacuate promptly because they have a history of this that happens enough that is something that's passed down from the generations, and that saved a lot of lives in Japan. And we are just trying to follow suit. So John talked about how we have the whole coast mapped. How many of you saw John's presentation? When were you here last and spoke? Oh, it was a while ago. Okay. So we remapped the whole, Dogami remapped tsunami inundation for the whole Oregon coast between 2009 and 2012, 2013. And we took the latest data, the latest geophysical data, the latest understanding of how subduction zones work. It was a team of scientists from all around the country and even a few international scientists to really try to get the most accurate picture of what the next Cascadia earthquake and tsunami might look like. Because the last one happened in 1700 and we weren't here to collect GPS data. So I'm not going to get into the nitty gritty, but you are all, John talked about the evacuation brochure, which shows a yellow zone, which is our XXL, which is the maximum considered local tsunami event. It's basically like a worst case. It's a very conservative estimate of how much inundation we will see. And then we also modeled a maximum considered distant event so a tsunami coming from Alaska. We're here today to talk about a local event. As you all know, this is the event that we need to plan for. There will be an earthquake and the tsunami will come within 20 minutes of that earthquake shaking. And a distant event is really just a beach event. It will require people to be off the beach. So we're going to be talking about evacuation from the XXL zone, but I just wanted to sort of remind everyone of that this is kind of the latest tsunami data, the most recent tsunami data available, and yeah. And there's more information that you can find out about this that I'll show you a link to later, actually right here. So John talked about this. There's many ways to get the information that we finished in 2013. We remodeled the coast. So in addition to what we call our XXL, we did 5 local tsunami scenarios: small, medium, large, extra large, and extra, extra large. So you can see what all those zones look like if you go to the website and look at the tsunami inundation maps. But you can also go and look at the evacuation brochure data. You can go and download the brochures themselves from the website. You can also, we have an online portal, which is a Google Maps based thing where you can punch in an address and see whether or not it's in the inundation zone, and you can start to plan your evacuation route. There's also an app, so if you, from the website, you can get a link to that app. It's available for iPhone and Android, and it's, it'll locate you, but you can also punch in an address and get information on which zone you're in. And our website is OregonTsunami.org. So, okay, so now that we've mapped the coast and we know this kind of worst case inundation area, we wanted to dig deeper and think about what is the most efficient routes for various communities. Sometimes it's quite obvious, like we all head up Lanita Avenue, but sometimes it's maybe not so clear whether to go one way or another way. And this is an exercise that can help illuminate that. It also allows us to really investigate the importance of things like bridges and whether or not they've been seismically retrofitted. Like in Seaside, some have and some haven't. So when you think about which signs you want to put on the ground, do you want to direct people towards the nearest bridge or maybe towards the nearest seismically retrofitted bridge? So this is a computer exercise where I can play around with these things and provide that information to the folks that are then putting those signs on the ground. So I've said this a few times, I'll repeat, this is a computer exercise, it's a GIS exercise, and basically what we're investigating are ideal routes, evacuation routes, this minimum walking speed, so John touched on this, so because we have then like a distance to safety, and we know when the tsunami arrives from our modeling, we essentially can calculate a speed, and that's the minimum speed that you must walk across the entire route. And this, I'll show you how that really comes into play in a minute here. But so I wanted to emphasize the most efficient route to safety is not necessarily the shortest. That's sort of the thing that this hangs on. So if you have steep slopes, that really slows you down. And also if it's difficult walking, like across loose sand, that's much more difficult to walk across than a paved surface. And so we collect that information for the entire road and trail network in a community to do this work. And so basically the routes that come out of that are based on this concept of the most efficient routes to safety, which is where some interesting results can come out of. That maybe there's high ground that's a little closer, but it's going to be kind of tough to get to, and there's so we look at these routes and these minimum walking speeds, and we also can use this to look at different hypothetical options. We can look at potential vulnerabilities. I can run it with and without a bridge and see how much it changes those minimum walking speeds. I can put in a hypothetical vertical evacuation structure and see how much improvement it brings to an area. For instance, a spit, which does not have a lot of high ground. And we're also, as a part of this, I'm not going to show any results today, we're looking at the socioeconomic spread of vulnerable populations in the community. So we're trying to sort of pair up the areas that are far from safety or have challenges getting to high ground, and then what communities live in those areas. So kind of a simple breakdown of the different census type data sets and putting them in the context of who's in and out of the tsunami zone and who's in these higher minimum walking speeds. So we put in, like I said, the quality of the road surfaces that we're walking across, paved versus loose sand on the beach versus a gravel trail, that kind of thing. We obviously put in the destination, which is, the XXL line. That's the goal. Where every road intersects with XXL line, that's a safe spot. And I will emphasize that's different than an assembly area, right? So we have assembly areas sprinkled around the community, and those are very valuable as places to come together after you've gotten out of the inundation zone and you want to go be with other people. But to survive the tsunami, you just need to get to green. You just need to get to high ground. And that's what's most important. So our work focuses on getting to high ground, not necessarily an assembly site like you see on the maps. And then also the key thing here that we have that's pretty unique are these wave arrival times. From all that modeling we did that we made the new brochures, we can determine wave arrival times for every spot in the community. And that's been really wonderful to take a look at, and it's really illuminated some interesting patterns and provided more detail about like how long it's going to take for, say, to go up into Nehalem Bay. So the products that come out of this work, there's 4 main products, and I know you can't read the words, they're too small, I apologize for that. But so basically you get these detailed, the first one up there on the top left is evacuation routes. We get detailed turn by turn, house level arrows that tell you the most efficient routes to safety. And these will be delivered with the report in GIS form for folks to look at, and we'll include them in some form in the report as paper maps so they can be looked at that way as well. And then those can be simplified. So you have these really detailed routes, like street by street, but then what we're calling evacuation communities are basically a simplification of those routes into which areas of town go to which safety destination. So am I in the part of town that heads to up Lanita Ave, or am I in the part of town that heads somewhere else? And it sort of just identifies in a more simplistic way which parts of town, maybe you take your own route to get there, but you know I head this way versus this other way. I think you'll get that a little more when I show you results. And then the third and most important thing here are pedestrian walking speeds. So this will look like, and you'll see results of this, it's basically a road map, same as you're used to seeing, except the roads are colored. And the colors represent this minimum walking speed. So the closer you are to high ground, the slower that walking speed's gonna be. And so yellow is a slow walk, and then it goes up to walk and fast walk, jog, run, sprint. And there are numbers associated with those, like there's mile per hour breakdowns of those, which I'll talk about. But so anyway, what it does is it provides this like visual where you can see really easily like, oh wow, that area is pink. Like everybody in this area has to jog and maintain a jog all the way from where they live to, the transfer station or whatever. So it really provides a strong visual to compare one community with another or one hypothetical scenario with another. And lastly, we'll provide information on the wave arrival time for the whole region. So this is an example of how you can compare two hypothetical scenarios and use these minimum walking speeds to showcase a really clear message of why, say, it would be important to retrofit a certain bridge. So on the left is a side-by-side image of North Rockaway Beach with Lake Lytle there. And so this is 101, and here's Lake Lytle, and on the south end of Lake Lytle is 6th Avenue, and on the north end is 12th, and then up just south of the high school on 101, there's a bridge, and on 12th Avenue, right off 101, there's also a bridge that crosses the outlet to Lake Lytle. So if you let the computer, if you say, yep, those bridges are going to be passable after the earthquake and people can use them, you run the model, it creates, this is an example of these watershed evacuation communities. So everyone within this black dotted line heads to 12th Avenue, and everyone down here heads up 6th Avenue. So it just sort of creates these neighborhoods where everybody within this blob here heads up to the high school. So it just sort of breaks the community up into these ideas. But then I ran it again and I said, nobody can cross that bridge and nobody can cross that bridge. What happens is it forces all of these people on 101, they can't go north to the high school, they can't go east across 12th Avenue. It forces them all down 6th Avenue. And so instantly you go from the light and dark orange, which is the walk and fast walk speeds, to purple and blue, which is run and sprint. And the sprint is that category goes from 7 to 10 miles an hour, which is a sprint. And so basically, so this is all in computer land. But the point being, that bridge is pretty important. Now, that's not to say that you couldn't scramble across the ravine that bridge crosses on foot. This is kind of a worst case scenario, but that's the point here, is to sort of identify that worst case scenario. So this is the kind of image where, the city could use this paired image in a part of a proposal to look for, FEMA funds to retrofit that bridge, justifying its existence by the fact that you can allow people a much faster access to high ground by heading north. And then the opposite, I can do the opposite thing. So I actually took this, I really didn't need this again. These are identical. So this is that without bridges scenario, but then I put a hypothetical vertical evacuation structure right off of 101 at 11th Street. And so it does exactly what you would imagine it would do, radially out from, I've brought high ground to the people. And so instantly you go from these very, very, run and sprint speeds back down to a slow walk and a walk. This is a very hypothetical situation. That would be quite the engineering feat to put a vertical evacuation structure in this exact spot. But it illustrates the point of, you can also use this to provide evidence of the assistance that a vertical evacuation structure would bring to a community. Should I define a vertical evacuation structure? Okay, so that means a structure that is designed to both survive the shaking of the earthquake and also survive the impact of the tsunami. So the repeated scour and debris hitting of the structure. And so it becomes a refuge that people can go to and remain safe and remain alive throughout the duration of the earthquake and tsunami. Yeah.
Even if you have that structure, how many people would it hold?
Right, so that's something that you have to take into consideration when you design something like that. And I have a slide where I'll show, we can talk about vertical evacuation a little more, but absolutely you have to think about how big it's going to be, what design it's going to be, who you want to be able to use it. So there are many limitations to this method for looking at evacuation from pedestrian evacuation. And the big one that we've actually started to think about and we're kind of looking at in a really simplified manner with this is landsliding and liquefaction. So liquefaction, this is a photo from the Christchurch earthquake of 2011. Liquefaction is a phenomenon that occurs when the earthquake is shaking and it ends when the earthquake is done. But what it does is it brings up sand and mud and standing water onto the surfaces that we will be using to evacuate. And so generally speaking, it will make walking across these roads where it happens very difficult, but it won't necessarily make it unnavigable on foot. It's also a very site-specific phenomenon. We cannot say exactly where it's going to be and where it's not. We do have, Jogami has maps of high versus low susceptibility for liquefaction, and I use that to consider a liquefaction scenario. But again, even that is really it's just an estimate based on soil type and bedrock type and slope and those sorts of parameters. So what I do for liquefaction is I basically take areas that have high liquefaction susceptibility, and instead of being a paved road, I change that value of paved road to loose sand. I make it much more difficult to cross. And as you can expect, it tends to make the results go in one direction. So those will be included in the report. We'll look at that sort of thing in the different areas where it has a significant effect on evacuation speeds. Landslides will be prevalent along the whole coastline because of the incredible amount of earthquake shaking that we will experience, 3 to 5 minutes of shaking. And so landslides, unlike liquefaction, landslides can remove a route altogether. We know this, it's happening right now in Brookings, yes. Right? North of Brookings. So this is a reality, and there will be places where roads will become impassable. But from my perspective, from getting us from the inundation zone to high ground in the period between the earthquake and the tsunami, I care about landslides that would remove a route that I need, completely remove it, that I need to get to high ground. So there will be lots of landslides, and maybe we'll even have to walk across some rubble of a landslide, but for the most part, I've only really worked with landslides in this process if it seems like a whole area is just going to kind of disappear and not be able to be used anymore, like some big scarp from some big known landslide. And I have to say that I could not really find any place like that in all of Nehalem Bay area. There are obviously mapped landslides along the back of Wheeler and around Nehalem, but the thing is, I think the reality is just that we can't say for sure where they will activate. And there are so many roads, like every road in Wheeler that goes off 101 pretty much reaches high ground. And so even if a few of them end up not being available because of some, slope instability after the earthquake, there are other roads nearby, and you're just going to have to make your way along until you can get higher. And so it really doesn't, it's not a situation where I took a route out altogether for landslides, but it is something that we're thinking about. So I should add here, I want this to be a conversation eventually. We'll stop talking and we'll talk about local issues, places that people are concerned about, places that people have been thinking about for evacuation, areas that might be tough, areas that you think are important. And, if there's some sort of landslide, for example, that you know about and you really think that, that might be a spot that becomes unusable after the earthquake, then we can talk about it. And I can certainly do a scenario where I remove that route. So that's open for debate. We have not started running these models yet for Nehalem Bay. And then there's other challenges that we're not able to really tackle at all, like down power lines. There's going to be lots of impediments to evacuation that we can't really acknowledge with Beat the Wave. This is really a planning tool. It's meant to kind of get a snapshot of maybe the lowest hanging fruit of things we might be able to work on to improve evacuation at a community scale. So there's lots of things that we hope can be done with this data. We're working with Meg Reed at the Department of Land Conservation and Development to put together facilities improvement plans in some of these communities to basically prioritize shovel-ready projects that can be put in for funding at a future date. And Beat the Wave images will be used as a part of those proposals to, like I was just showing in Rockaway Beach, to just show how important, that project might be. And so there's that kind of thing. And there's also, you can use this for wayfinding, deciding where to put signs in your community and which destinations you want to direct people to and which roads you want to direct people to or away from. And so these are photos of, let's see, wayfinding down here. There's different kinds. There's blue lines, which you guys have in your community, marking the edge of the tsunami zone. And then there's also places like Cannon Beach have put signs within the inundation zone, directing people out at a very dense network to help people get out. And up at down in Safe Haven Hill in my town of Newport, down at South Beach, there's a place called Safe Haven Hill. It's the only, it is currently the only refuge for all of Hatfield Marine Science Center, the OSU's marine campus, and South Beach State Park, and the aquarium. And so it's been improved. It was always out of the inundation zone at the top, but it was covered in trees and blackberry bushes and transients. And the city leveraged funds from DLCD and urban renewal funds and built trails, several trails, so you can access this from several directions. And they cleared the top and made it like a nice park area, and they put a cache up there. And so they're just making it, and they practice evacuation drills twice a year at Hatfield. And then on the right are vertical evacuation structures. So the first one of its kind in the States was finished a couple of years ago, and it's up south of Westport, Washington, in the Grays Harbor area. It's the Acosta School. And so in that case, it was designed, it's the roof of the gym, the actual tsunami vertical evacuation structure. And it was designed to accommodate both all the children and faculty at the school, but also the community surrounding. It was designed to be large enough to hold as many people as would potentially be able to reach it and use it. And more recently, right now, they're building a vertical evacuation structure at the Hatfield Marine Science Center. It's the newest OSU building, and it is being built in a different manner than the Acosta School. This is a schematic of what it's going to look like when it's done, but it's going to be a really big ramp on the outside of the building that anyone is allowed up that will go to the roof, and the roof will be the vertical evacuation structure. So folks in the building can access the roof, but you can also, everyone in the area from all the other people that work down there and visit down there will be able to access it as well. And there's a webcam. You can watch it being built if you go to OSU's website. So any questions about that? Yeah.
Does any of the data modeling substitute a walking value for use of a vehicle for evacuation?
No. We do not expect use of a vehicle to be realistic at all because of all these things I talked about: liquefaction, landsliding down power lines, your adrenaline. We just don't think it's likely that a vehicle will be helpful at all.
Earthquake, but what about a tsunami?
What?
The vehicle use.
Well, so the
Earthquake, but a tsunami, that it could just be a tsunami. We get these tsunami alerts. It's coming. It's not saying that there's going to be an earthquake. It's just saying there's going to be a tsunami.
So a tsunami that doesn't have an earthquake preceding it is a distant tsunami. So somebody else got that earthquake, Japan or Alaska or Chile or New Zealand. And it takes many, many hours for those tsunamis to reach our coastline, 4 at a minimum from Alaska and 11, 12 from Japan. And it's not nearly as significant a level of inundation. It's really just the beaches and the really low-lying areas. And especially up here, it doesn't really flood any of our roadways except for, you know, the ports, kind of. And so in that case, evacuation will be very limited in who actually needs to evacuate, and then it could be done by vehicle. But
Remember, for the distant event, you're only focused on that orange zone on your evacuation. If you're in that orange zone, then yes, you should probably evacuate from the ground. You don't need to drive to the valley, because you can do that. So, you know, you just need to be mindful of which zone you're in. And again, know where high ground is, know where safety is.
yeah.
But Laura's point earlier about being able to evacuate from a local event, you need to put that out of your head right now. Driving out of our zone in a local Cascadia event, it ain't going to happen. You will not be able to drive out. You probably won't be able to even get your vehicle out of the garage. That's the reality of the situation. And to be honest, people will die if you're spending time mucking around trying to get your car going and finding routes out. You need to be moving as fast as possible on your feet and know exactly where you need to go. That's how you're going to survive.
And, oh, go ahead, Linda. Oh, hi, yeah.
Your thing, what you're talking about, there are two parameters you're dealing with. One is the maximum wave height, and the other is the time for wave arrival. How accurate is that, since Japan underestimated the strength of the earthquake potentially, and their structures weren't built high enough, nor were their walls?
Yeah.
So how accurate are those two parameters?
Well, we won't know exactly until we, but no. So, you know, actually when Japan happened, when that earthquake happened, we had just finished up remodeling, and there was actually some pushback on our XXL because it was such a big earthquake. And people were, the scientists, you know, reviewing it were like, this is crazy, you know. And then Japan's ended up being much larger than even, you know, very educated scientists studying that subduction zone expected. So there are significant conservatisms built into our model, especially in that highest XXL earthquake scenario. And so it is just a model, but we built in several conservatisms in order to try to capture that worst case conservative scenario that we, you know, hope will not supersede. We didn't include friction, so the wave doesn't feel the landscape. It doesn't slow down due to going over land, which we know is not realistic. In reality, the landscape will slow the wave down. We did not model tides. We held it at a static mean higher high water tide, which is a relatively high water level to start your tsunami on. We also rounded up on the amount of slip on the earthquake, more so than we've seen in the 10,000-year record of earthquakes on this subduction zone. We rounded up from the biggest one we saw in 10,000 years to it's a bigger earthquake than this subduction we think has actually done in the last 10,000 years.
What about the wave arrival time? Because I've seen different numbers on that.
You know, We don't know. I mean, we're the only ones that have done that, really. So we use a hydrodynamic computer model. We don't do it. We have an expert who works for Virginia Institute of Marine Science on the East Coast who does the modeling for us. And it's modeling, but it's been extensively benchmarked against real observations in other tsunami scenarios. We used the 1964 Alaska earthquake and tsunami, which we received on our coastline. So we used actual water depths at various locations that were known from that event to turn the model to make sure that it was reflecting reality as best it could. So we're not, I wouldn't hang my hat on it down to the minute of when the wave will arrive, but we feel that it provides a very realistic understanding of generally, of when the wave will arrive in these communities, if that makes sense. Yeah.
I assume the travel times to the high ground are based on being fully dressed and ready to go. A person could have 5 minutes of that time just getting organized. So
that is a fabulous lead-in. So we take that into consideration. It's one of the conservatisms built into what we're doing. So there will be 3 to 5 minutes of earthquake shaking where we will be under our chairs, just waiting it out. And then we will need to get ourselves together. This modeling starts on the roads, and we're obviously not hanging out on the road right now. And so we call it milling time. It's this idea of surviving the earthquake, drop, cover, and hold, and then getting your bearings. You're going to be in shock, maybe digging out from a sign that fell on you, or, and getting out the door, which might be, jammed because of the earthquake shaking. So we do a 10-minute delay. So basically I take 10 minutes away before I let people start walking in my model. So I wouldn't say it's conservative. I would say it's pretty realistic, and it could be longer than that depending on, but that's an educational thing too. Some of it's just, it is what it is, but some of it is, one of the messages that we feel is very important that comes out of this is prompt evacuation is so important, especially in areas where high ground is pretty far away. The more you dawdle, the less likely you are to survive.
Is that 10 minutes from the beginning of the shaking or the end of the shaking?
The beginning.
Beginning. Okay.
Yeah. Yeah.
The deliverable of a lot of the work you've been doing are routes. In this community, average age 58, mobility is a very big deal. The routes and the times, obviously, for a 16-year-old are a little different than a 17-year-old.
That's true. And so, but also the 16-year-old could have a broken ankle during the earthquake. So you're right that there are mobility issues with different age groups, but there's also the reality of what could happen to any of us during the earthquake. We could be injured, or families trying to bring kids with you will slow you down dramatically. So there's lots of reasons why different speeds are unattainable for certain groups of people. And the results, which or I guess we already showed, but I'm just gonna go back to here where, so the light yellow is a slow walk, and the orange, so this is slow walk is the yellow, and then walk is the orange. And that break between the walk and the fast walk is 4 feet per second. And 4 feet per second is about 3 miles an hour. And that is the speed with which transportation engineers use to time crosswalks. So it's meant to be a pace that nearly everyone can make it across the street before the light turns. So it's meant to be sort of a lowest common denominator speed. And so one of the things we look at with the socioeconomic analysis piece of this is if I can break out where the 65 and older age population is, and if they're in an area that's outside of the slow walk or walk, that flags it for me, as an area that needs to be, there's nothing I can do about it, but I can point it out, and maybe there's high ground nearby that isn't currently attached to a road or a trail, and that could be something the city chooses to invest the money into developing a trail with some signs to make high ground more accessible for a community, for a neighborhood. Yeah.
Can we factor in the adrenaline factor? Those oldies of us, maybe will get a little more pep in our step.
The more pep, the better. Yeah.
That's a bonus. What elevation are you now modeling to?
Okay, another great question. So the elevation, what's called the run-up elevation, the elevation to which the tsunami will peter out and stop, varies very dramatically along the coastline of the state. It also varies greatly between an open coast location and inside an estuary. So here in Manzanita on the open coast, it's anywhere from like 70 to 90. There's even a few spots where it's like 95 or almost 100 feet where that wave runs out of energy. But back in Nehalem, you're already down to like, I forget what it is exactly. I wrote it down. In Nehalem, it's downtown, it's like 30 feet, 30, 35 feet. And then in Wheeler, it's like 35 to 45 feet above sea level. So it really varies depending on where you are. Yeah.
I have a question about Wheeler. We have some concrete block buildings that were built in '39. Should we try to get out of the buildings immediately? If we can, when it starts shaking?
Yes.
Like City Hall.
Yes. Yes, those unreinforced masonry buildings, this is something that's being talked about at the Capitol right now. The reality is that these buildings will be severely compromised during the earthquake shaking. And the official message is to drop, cover, and hold. But if you are able to not, because there's the concern that you would injure yourself more trying to get out of a building than just to stay put. But at this point, that's a personal decision. But there is a case for considering.
It's a legitimate concern that
Yeah.
There are going to be things flying off the ceiling that you could be hit with. So it's one of those factors that you have to weigh up, take into consideration. I agree with Laura. I mean, it's emergency managers will say emphatically, your first objective is to drop, cover, hold. You will be protected under a table. But then on the other hand, if the building is questionable, then maybe if you can get out as quickly as you can.
I thought you'd be shaking so badly you couldn't walk. Is this not true?
Well, that's one of the other. It's going to be tough. It's definitely tough standing up. There's no doubt about it. I mean, the forces are pretty significant. That it would make it challenging. Yes.
It is different than a strike slip fault, like the San Andreas, creates a much higher frequency style of shaking. Those earthquakes are much, much closer to the surface. And it's like the China inching, shaking off the shelves. And this is going to be, not that I've experienced any earthquake myself, but just from reading, it's like really long wavelength shaking. So it's still like the G's are phenomenal, and it will be difficult to walk, but it is very different than the California style earthquake. Yeah.
So the other thing about Wheeler, we have a large tide plain that makes the bay. And then at the end of that, we have big crevasses where the creeks come in. How does that affect how the wave behaves?
Well, the modeling was done using a very high resolution LiDAR DEM. And so it sees all of those sloughs and ravines, and it's allowed to do whatever it wants to do following the fundamental principles of water movement. And so it sees those and it goes up them. And I was looking at, flow depths and run up just in that spot, and it is deeper there and it goes up there, but you also don't have infrastructure there really. It's like kind of gaps in between the roads and the houses because they're ravines. So yeah.
Are you saying your modeling is done for the Nehalem Bay area, or are we starting a process?
I should be careful. There's two kinds of modeling. So there's the tsunami inundation modeling, which we finished several years ago. And that's what was used to create the evacuation brochures and the tsunami inundation maps. So that's the XXL. So that hydrodynamic tsunami modeling is what I say had a LiDAR-based DEM. And but now what I'm doing is evacuation modeling, which is also modeling, but it's taking that zone of XXL and then doing this totally separate work on it. Does that make that clear?
So when would that be? When do you expect to be done with that, and will there be any community engagement in the process?
That's what this is. So we'll get to the local issues in a couple minutes here. But so yeah, this is like a kickoff meeting. We've met with some stakeholders, EVC and So the point is to just make sure that, local issues have been fully acknowledged before I dive in and start doing all these hypothetical evacuation scenarios, because I want to make sure that the end result is a product that, the public and planners and emergency managers will find useful.
Well, and the final report will be August 16th, where you guys are coming back on the 16th to talk about the final product.
I believe you.
Yep.
I believe, I believe that we have to have the report published from this work was funded by NOAA through the National Tsunami Hazard Mitigation Program, I'll add. And I believe we are September, August 31 is when so yeah, we will be publishing around then. Yeah.
Regarding the hydrodynamics of the wave itself, as an old surfer, I can envision when the wave hits the end of Neocani Mountain and it sticks out at 45 degrees and those are cliffs, it's going to build on itself and go laterally south, really fast and really high. I'm just, that's what comes to my mind.
So again, the modeling can actually take that into account.
Yeah.
The physics for the actual flows of the water as it interacts with the terrain, high cliffs and things like that is actually very well established. To be honest, the biggest uncertainty in the modeling piece really goes on actually out at where the actual earthquake starts. That's the part that is really the most challenging to develop the underlying geophysical model that drives that. I mean, that's the part that we have to make a lot of assumptions about. But certainly the modeling that takes the wave and brings it onto the land, that is really, really well established.
Yeah. Well, typically when the waves are real big, 20 to 40 feet, we see a lot of lateral action.
Sure.
And a lot of, swelling up.
And you can actually, if you go to the Oregon Tsunami Clearinghouse, so it's oregontsunami.org is kind of a quick search, you have to sort of burrow down, but there are actual animations that were developed. There are several there that are really high resolution, really excellent animations, and then there's a bunch that are not so good. So it's worth taking a look at that. And I'm pretty sure there are animations for this area. That I know certainly there were some high resolution ones developed for Cannon Beach. I just can't remember specifically about Mahalen Bay.
But what they show, which is really cool. So yeah, if you search for Oregon Tsunami and then the word animation, it should take you to the right page. And so yeah, some of them are kind of crude, but even the crude ones, they're pretty fascinating. I'm sorry I don't have one in the presentation. They sometimes are a little clunky, the video. But they show a wave coming in, and it comes in as kind of a line, a simple line, because the earthquake fault offshore is a line. But then it comes in and it hits the coast, and it interacts with Neocani Mountain. It interacts with the coast itself and bounces off, and you end up with like slinky effect of like waves kind of slinking their way up and down the coastline. And features like Neocani Mountain do affect that stuff, and it's fascinating to watch. And then also, the waves enter the bays and then start ringing like a bell in the bay. So water gets kind of trapped in the bay. So, tsunami waves come in at regular intervals every 30, 45 minutes or so, and then recede back out again. But they come into the bays and then don't necessarily come back out again all the way because it's, trapped. And so they start stacking. And so another thing that there's available on our website are time histories, where at a single location, if you go to I'm not sure of the quickest way to get to this information. We can think about that a little bit, but you'll see a time history of over the course of 8 or 12 hours, however long we ran the model for. You can see those water levels, and you can see the first wave come in and do something really simple, like it comes in and then it goes out. But then it comes in and it kind of stays up and does some wiggles and then goes up again. And it has really complicated wave patterns, especially inside the estuaries.
Do you take into consideration the flow of the river as well? Because that's a reactionary issue.
Not for this modeling, no.
Okay.
We have done that for new modeling that we recently completed up on the Columbia River for maritime purposes, where we actually are incorporating more the fluctuating tides, the role of different river flow regimes. We actually incorporate friction there. So it's kind of the next generation modeling that we're doing now, but for evacuation purposes, for life safety and for just the fact that we're actually built so much conservatism into these existing models, it's probably not necessary. I mean, reality is what we've shown on the Columbia River is the impact from, say, a 100-year flood plus a tsunami, which when you think about it, the joint probabilities of those events occurring together is pretty extreme and far out there. But the actual contribution is not a lot in a big system like that. So
it won't build up. Okay.
It builds up a little
I mean,
bit,
it builds up in and of itself.
Right, but it's not going to push water
No.
further out. Okay.
Here, we'll.
Geophysically speaking, what kind of elevation change do you expect here with the earthquake? With the resulting drop?
So the subsidence that will occur coast-wide will vary depending on where you are along the coast and how large the earthquake actually ends up being. So the subsidence associated with an XXL event in this part of the coast is like 6 to 10 feet. That's not something we'll notice because we will drop as a collective whole region. But it will be something that we'll notice long term because sea level, relatively speaking, will be different. Yeah.
How long from the first wave of the tsunami, I know it goes back out again, how long is there a typical of how long they continue to go on like that?
We say that you should remain outside of the inundation zone for 12 to 24 hours because truly the wave continues to be seen in tide gauges for 24 hours and greater. It goes around the globe, but the extent to which it's continuing to come back across the landscape and not just staying in the river channels, it can be as much as 12 hours or even more, depending on the local what's happening locally.
But after the first wave, is that generally the furthest inland that it will go?
No. It really depends on where you are. So like in these bays, things get really weird really fast. And so, water levels can end up higher a couple hours into the scenario than right away.
Because it won't go all the way out. But along the coast itself?
I wouldn't want to promise that.
So typically what we're seeing is that the worst of the conditions typically within the first 6 hours. The wave is starting to peter out after about 14, 15 hours. And by 24 hours, it's kind of noise that very negligible conditions after that. But Laura's right. I mean, it'll actually continue to resonate for a number of days after the event.
And can aftershocks trigger subsequent?
Unlikely. I mean, it's possible in the scheme of things, but an earthquake has to be at least a 7 to even think about triggering a tsunami. And aftershocks can be that high, but I don't believe there's been anything more than maybe a really, really localized small tsunami generated from an aftershock of a subduction zone earthquake. Yeah.
So there's one big wave and the potential for a series of others? Or?
They continue to be, coming from the subduction, from the fault offshore, they just keep rolling in. They're the same size, they're petering off slowly, but they just keep coming in. The first one has the most energy, so it is the biggest, but the next ones that come in continue to be significantly large.
So the largest wave is typically within the first 20 to 25 minutes at the open coast.
Yeah.
And the biggest waves in general are within that first hour. But then, as Laura's pointing out, as you get into backwater areas up in estuaries and things like that, the biggest wave may not necessarily, in those locations, may not necessarily be the same first wave that came in. It could be some hours after the fact.
Because the thing is, even offshore, the wave is starting to feel the bottom. It's starting to feel the sandy bottom on the continental shelf, and they slow down, and then the next one catches up to it. And so they build, and they even start doing weird non-simple wave type patterns, as they're approaching the shoreline. And so that's why it's not super simple. That pattern of inundation is not, that simple because it is interacting with the ocean bottom as it's coming in.
So there's no set amount of waves, it's just you can't really predict how many there would be.
Correct. Yeah.
The Cascadia Fault is very long. Does the whole plate shift or different pieces or?
A great question. So will the whole fault go or will just a piece of it go? Both are possible. There's geologic evidence that there have been many partial ruptures of the Cascadia fault line, predominantly on the south coast from the Triple Junction in Northern California where the plate begins, where the boundary begins, all the way up through, like Florence, really. Even further south than that is where it peters out from a lot of activity. But so it looks like there's twice as many earthquakes in the historical record, the 10,000-year record on the south coast than on the fault line as a whole. Both are possible. It's possible the whole thing unzips. The earthquake from 1700, our most recent Cascadia event, the whole thing unzipped from Northern California to Vancouver Island. But there are partial ruptures that have happened many times, and they create a local tsunami. Basically whoever's on shore from where it ruptures gets what feels like a local tsunami. And those they will be experienced elsewhere along the coast, but it'll be a lesser event.
So on the south coast, it on average, it's about every around 230 odd years. So the chance of a south coast rupture is much higher. Estimates are as high as about 40-45% in the next 50 years of an event like that taking place. So there's a strong possibility that we could experience certainly a south coast event in our respective lifetimes.
Would that be considered a distant tsunami?
That's a good question.
We've been debating that.
Yes, if you're up in Seaside, because you probably wouldn't feel that type of event. The modeling that we've done seems to suggest that somewhere around Cape Lookout is probably the northern limit of feeling the actual earthquake shaking. And then so north of there, it would be effectively a distant type event scenario. So in that respect, you're going to hear about it via CNN, Twitter, Facebook, all that sort of stuff. And obviously the warning centers will have issued their warnings within typically they'll issue a warning, they'll make a decision within about 5 minutes, and we'll have an initial warning out at around 10 to 15 minutes. So you'll hear about it through that way as well.
Yeah. But it would be designated for our local areas as distant?
It would be, yes. It would be more like a distant type scenario, correct.
Yeah, the inundation would look more like a distant scenario.
The inundation is not dramatic. So I think as a minimum, I would be moving at least out of the orange zone, probably going a little bit further just to be on the safe side.
And what percentage is it here that we might have the earthquake tsunami?
So the potential for a full margin rupture is estimated at around 15 to 18% chance in the next 50 years. So again, those are pretty high odds, and it's something that we need to be collectively being mindful of and planning towards.
Would you repeat those numbers, please, Jonathan?
Around a 15 to 18% chance in the next 50 years, and that's been estimated by the U.S. Geological Survey.
You said you're about to go ahead with discuss local concerns. This morning I had this fantasy, I hope it's just a fantasy, that I'm on the beach with the dog when it happens. What's that going to feel like?
We were just talking about this today about liquefaction and the realities of what liquefaction will feel like during the earthquake on the beach, and we don't really know. The problem is in these really massive subduction zone earthquakes, we don't have anecdotal evidence of what happened on those beaches. So we think liquefaction will be experienced. It's saturated sediments, so it's possible that it will be difficult to move.
So would it be like quicksand?
Yeah, so liquefaction only happens during the earthquake, but yeah, if it quicksands during the earthquake and you kind of get stuck and then it's over and then you're kind of, stuff. But we don't know, but we're not saying that's going to happen. We're still trying to answer that, you know? We don't know.
So those are excellent questions, and
yeah.
We're continuing to try to find information that can actually help guide us with answering those types of questions. You know, particularly from places like Japan and Sumatra and Indonesia experiences. But unfortunately, there's just not a lot of information out there about these types of experiences.
Well, I mean, to be fair, even if you could tell me, it's not going to change.
What do you?
Okay, now I know what it's going to feel like, but.
Yeah.
Still gonna walk.
It's
still gonna walk.
Still gonna walk the dog.
Oh yeah, walk the dog.
Wear snowshoes.
Wear snowshoes.
So I spend quite a bit of time on the water. I fish and hunt a lot. I fish offshore a lot. So if I'm fishing, let's just use a hypothetical example. I'm halibut fishing off the coast here, and I'm about maybe a mile offshore. At that point, I'm assuming if I'm out there in my boat, I'm going to notice some type of unusual surface tension issues going on with the ocean.
This is a great question. You guys are like exposing all the work we've been doing. It's wonderful.
So, at a mile offshore, can you see the shore?
Oh yeah.
Right.
Oh yeah.
So, some telltale signs could be things like a sudden change in the boat itself, as in sudden impacts of change in currents, vessel shifts. You start to see discoloration in the water as it becomes more turbid. Certainly, a telltale sign from the shore-based side of things is that you'll probably see significant dust appearing along the landscape as landsliding takes off. And so a great example is if you had a look at some of the videos that were collected around Palu in Indonesia just recently, several weeks ago, which had a major earthquake down there. And there's some phenomenal footage from the ocean looking back on land, and you just see this billowing dust cloud along the coastline as landslides took off. So those are all the telltale signs. So your question about where do you go? For a local event, you would need to, our recommendation is to go to at least 100 fathoms. Okay. So that's for a local event. For a distant event, so something happening up in Alaska, a big event up there, then you want to go to about 30 fathoms.
Any deeper and you will not become entrained in the
and so the idea
wave.
there is basically to get away from the potential effects of strong tsunami-generated currents that would be operating at shallower depths. So we've done all.
You want him to go further out?
Yes.
So, but the thing is, if 100 fathoms is miles away, then it becomes it's not obvious,
So from work we've done on the Columbia River, our recommendation is up there is that you want to be going to at least 80 fathoms depth. So anything shallower than that, you are likely to experience very strong currents. If you are fishing halibut, say down around Stonewall Bank, you want to avoid Stonewall Bank altogether because that's an area that creates tremendous amplification and extremely strong current. So you want to be avoiding that area altogether. But the point is, your main guidance is to point your vessel seaward and head out into the waves, into as deep a water as possible, and just be mindful of the fact that you probably, for a local event, you'll not be getting back into any of the ports and harbors.
So then if we're fishing at the mouth of the bay, okay, which is very popular July, August, September, and I think a lot of people fishing right at the jaws, right at the mouth. My thought has always been, if I notice, obviously undulations of the soil, land, etc., there's an earthquake going on, just to run in to jetty, abandon the boat and head up the hill.
Yeah.
So we have about 20 minutes to do that, which is typically not a problem. But
So just be mindful that you're talking about mouth of Nehalem Bay here. So, again, you need to do the math. in terms of time it's going to take you to get back into the harbour and into the bay to get to that high ground point. I mean, I think that's something you're thinking in the right direction.
There's a right at the mouth.
Right, so my only question mark would be that the conditions at the mouth there are not going to be the same. That jetty will probably collapse. And so you're going to be dealing with a very highly dangerous environment potentially after the event, with waves breaking over different features, and so it's going to be a much more challenging condition coming back into that type of environment. So you need to be mindful of all those factors, but you're thinking in the right direction. You're trying to weigh up all these different decisions.
And there's some more information on our website. There's like a page devoted to maritime guidance that we've been starting to put together.
The wave arrival times, is that from the initial start of the earthquake?
Yeah.
Okay.
Yeah.
So when you're talking 20 minutes, you're talking potentially 15 minutes from the time the ground starts shaking until the wave hits.
Correct. Yeah.
What's the best source to get a text on my phone that there's been an event?
There will be an earthquake.
No, I mean, let's say it's a distant event.
Yeah, a distant event. Okay.
Good site to.
So you can actually you can sign up through the National Weather Service, I think it is. That's an option. You can. One of the things that there are apps that provide you with information about earthquakes that are taking place around the world. There's obviously a very extensive seismic network. I use things like that.
I've got one of those, and there's been a couple of distant events that I never got notice of.
Okay. So there are some apps that are better than others. We do have a smartphone app that Laura mentioned earlier for tsunami, to basically identify whether you're in the tsunami inundation zone or not and where to go. That version currently does not have direct links to the Alaska Tsunami Warning Center, which is our main warning site, but we are building that capacity. So we anticipate having that capability built into it, hopefully by the end of this year. And so what it would do is that, let's say an event takes place in Alaska or Japan, and it's a big one, and it's a tsunami warning has been issued for the Oregon coast, then it would actually push that message to you. So we are working towards having that capability. Certainly for distant events, again, the nearest one to us is Alaska, which is about 4 hours, less than 4 hours away. Japan is 9 hours and 30 minutes away. And those are the two biggest areas that we worry about. So you have more time to find out about those events, and you're going to hear it through the radio and other mechanisms.
But the National Weather Service is a good place to start. Right. Go to their website, and I think that's where I signed up. I started there and ended up signing up for tsunami warning notices.
I read recently that the U.S. Congress is considering a bill to establish early warning for earthquakes on Oregon, Washington, California. Do you know anything about that?
Yeah, this is an ongoing project that's being worked on by the University of Washington, University of Oregon, OSU. Dogami's been a small part of this, and this is something that other countries have been doing for a much longer time, and it's basically building out a very dense seismic network and the capabilities to interpret these signals, the very first earthquake signals that start after an earthquake starts, and understanding what the event is going to be, and then being able to push that warning to people's cell phones. It's a very, very complicated and very expensive undertaking that already has federal and state dollars, but they've been getting it in pieces, and so they're always working on getting the next piece, and so they're constantly building it out. And
so just remember, it's really fundamentally orientated towards being able to stop a train,
yeah, or
to halt a lift, or to provide heads up to someone who's performing surgery that an earthquake is coming. I want to reinforce the point that from our standpoint and our messaging for your preparation for a local event, the message is simple. If you feel strong ground motion, strong earthquake shaking, and it's lasting more than 2 or 3 minutes, you're into the big one. And that is your warning, and that's the triggering mechanism for you to get to high ground as fast as possible. You don't wait for anything else.
Yeah, so the earthquake early warning, depending on where the technology ends up going and the type of earthquakes that happen, it'll be like 10 to 30 seconds of warning. And so the point is, for those automated things like shutting off a natural gas main, stopping somebody with a scalpel from like going somewhere, he has time to like pull it out, it's that kind of thing. But there is footage of in Japan and in Mexico where they have these capabilities. And in fact, there's footage from Mexico from their earthquake they just had recently where somebody's like filming on the street and it's like a nice, normal, happy day. And all of a sudden people start running out of buildings even though nothing has changed. And then like 20 seconds later, an earthquake starts because they got warnings on their phones. And so it's technology that other countries have. They have different geographic, the ability to do that. It's not quite the same as what we've got going on here. But so for the most part, this is for major systems and not for individuals. But it is something that they're pursuing at all levels, and eventually it might come to the public.
A 1 minute earthquake seems like an eternity. I cannot fathom a 3 to 5 minute earthquake.
Me either.
How long would the big one last?
3 to 5 minutes.
So on the footage of Japan where the big debris slide is moving across, it looks like lowland. It looks like it's moving pretty fast. Do you have a miles per hour on?
I think you're talking about Palu in Indonesia, just the one.
No, I'm talking about the Japanese tsunami.
You mean the actual of the wave itself going?
I saw the mud flow and the debris flow, which looked like it was moving pretty fast.
Yeah, it's about 30, 35 miles an hour.
Okay.
So our modeling doesn't take into consideration debris entrainment, the tsunami modeling. But generally speaking, the water is going to move as fast as it wants to go. But so this slide actually is the wave arrival times for an XXL tsunami, modeled tsunami in Nehalem Bay. And so it's sort of a lead into that question. So I don't have a close-up, but when the report comes out, you'll be able to see this in finer detail. But so in Manzanita, generally speaking, blue to red. So blue to yellow to red is the earliest to the latest wave arrival. So even without it being an animation, you can see it hits the beach in 20 minutes. That's the darkest blue. And it reaches the back of Manzanita by about 30 minutes, something like that, 28 minutes. But then, it keeps going up the bay. So it doesn't actually it reaches Wheeler in like 30, 35 minutes. At Nehalem, the same, and by the waterfront there, it's even a few minutes later than that. And then it just kind of keeps slowly trucking over, continuing up the estuary. And so, even where it peters out, it takes over an hour for the wave to, keep heading upstream. I mean, it doesn't reach Cloverdale, that's outside of the inundation zone, but it's heading in that direction, and it's over an hour.
Where does that relate to height of tide?
Oh, like the head of tide?
Yeah.
I don't know where head of tide is in this system. I have no idea. It's well past Molar. So Molar's down here. I'm trying to think in Newport, I think head of tide is further upstream than the tsunami goes. I think head of tide is like really far upstream in Yaquina. But
is Aldervale, which is right where North Fork Road, just about where it meets 53 in Aldervale.
Here's 53.
North Fork, which is the valley there.
There's the North Fork.
Going all the way right there.
Oh, so it's at that's head of tide right there? Okay, so it's basically at head of tide is where the tsunami runs out of steam for the XXL. Yeah.
A lot of the Neocani neighborhood is on an old slide that's, I don't know how many hundreds of years old, but what do you know about that?
That's about what I know. But so, I was sort of talking about how, from a beat the wave perspective, when I look at the Neocani. What? Sorry?
Liquefaction, more slide.
It's up on the hill slope. I'm not actually concerned about liquefaction up there, but I do think the reality is that there will be slope failures of some kind in that neighborhood. But I wasn't able to really account for it in Beat the Wave modeling. That most of the neighborhood is out of the tsunami zone as it is. So from my perspective, where I'm looking at which roads are in the inundation zone and going out of it, there isn't much to account for.
So in all reality is that the potential for sliding along a lot of this coastline is going to be enormous.
Yeah.
Again, if you think of what happened in New Zealand a few years ago on the South Island there was something like 5,000 or 6,000 landslides along a 100-mile stretch of coastline, and that was a high magnitude 7. We have an extensive landslide network along our coastline. Our lands are steep and unstable, and so that's the reality. It's probably going to go. And yes, you're right. I mean, a lot of these features are older landslide blocks that are probably going to be re-triggered.
Yeah, there's a thought that slides that actually perhaps were triggered in the 1700 event have not moved since then, maybe, but we can see evidence of them in the landscape, and they're probably more easier to reactivate than some fresh slope, right? There's already some plane of weakness, even if it hasn't moved in 300 years or more.
So if it happens in the wintertime when we've had a lot of rain and the ground is saturated, I mean, we get slides along the highway all the time now. Is it going to be much worse then?
Yes.
That's what I kind of thought.
Yeah. Yeah.
Now we're talking worse.
Yeah.
Yeah. Yeah.
So, do you have more sort of detailed Beat the Wave kind of info on later slides?
So this is
time conscious, and I don't want to.
So no, actually I don't. So this is like a kickoff meeting where, thank you for the lead-in. Again, you guys are perfect. So I don't have results to show you today, and that's because I'm getting ready. So I've been, Fletch and I have been, who's our colleague working on this with us out of our Portland office, have been putting together the road and trail network. This is the most important piece. And then taking that road and trail network and deciding what we're going to do to it, which bridges we're going to chop out, which vertical evacuation structures we're going to put in, which trails we want to add, anything we want to do. And so this is where we want to make sure that, you guys know this community much, much, much better. And so the point is to talk about, things that you know about, things you're concerned about, trails you know about, some footpath that, all the locals use and it's not on any map. I'm not saying I'll put it on a map, but, any details like that relating to evacuation. Yeah.
Well, just from your gut feel from what you've seen so far, is there a need for a vertical structure here in this region?
So we'll, maybe.
So let me. I think the answer is maybe if you're in the Halem State Park. I mean, that's probably if you look at this area here right now, probably high ground is sufficiently close by to most areas.
Yeah.
So that's a great thing. You're very fortunate relative to some other communities. But it's the folks who are camping down at Halem State Park there who are really probably in the highest risk in terms of finding suitable evacuation spots.
Yeah.
They've got to travel a little further. So that would be, I think, logically speaking, that would be the one site that, you might play around with those types of scenarios.
And when you're talking about vertical evacuations, there are options besides building.
Yes,
Correct.
thank
Yeah,
you.
I mean, you could build mounds, you could build towers.
Long Beach Peninsula in Washington, I don't believe they actually have the funding to do it, but they've designed a mound type structure. So it kind of has I'm assuming it's sort of, maybe not riprap, but some sort of seawall. It's like a park, but it's elevated and it's at a high enough elevation based on the modeling that was done up there to, be a refuge for people. But it's not a building, it'll be outside. It'll be like you're hanging out on a man-made hill. And in the meantime, it's a park. Like now, before an event, it becomes a usable space. Yeah.
The work you're doing with this plan, is it in conjunction with what Meg Reed is doing?
Yeah. Yeah, so we're actually not working with Meg in Halem Bay, but we're working with Meg with DLCD in many, many other communities, including all of the unincorporated communities of Tillamook County, and Meg is working with Linda and talking with the city of Manzanita and Tillamook County about doing some of this work in Manzanita as well, her land use planning work for
Meg's
tsunami.
working in Rockaway Beach.
Yes.
With us, so.
Yes, yeah. And we did Beat the Wave modeling in Rockaway Beach, again, separately from Meg, but she's using Beat the Wave results with Rockaway Beach to consider tsunami resilience efforts through land use planning. Okay, so my list of things that I came up with for things to consider for Beat the Wave. So first up is always bridges. I always think about bridges first. And actually, they are not, in my opinion, and I'm open to suggestion here, there are several bridges which are not built to withstand the shaking of a Cascadia earthquake. However, people don't really live in between them for the most part. So, you know, there's Highway 101 across the river, and then as you come down into Wheeler, there's both where it crosses a slough and then where it crosses the railroad tracks. And that's actually a pretty significant drop, even though it's technically not over water and, you know, maybe you could scramble. But, you know, other than the boat launch, which I know can be very popular, but this is an uninhabited stretch of roadway in between. And so when I think about evacuation, I think about a bridge. Is it needed to get people from where we are right now to where high ground is? And in this case, I feel like all three of these bridges don't meet that criteria for me, because everybody's either already in Wheeler or already in Nehalem. And those bridges are not critical for evacuation purposes. They may be critical for post-event recovery and connectivity between the communities, absolutely. And the same sort of goes to the other bridges I identified that I will consider being available and then consider being unavailable is over the North Fork on Highway 53 and McDonald Road up to the north there. And that's it. So if anyone points out anything I'm missing on that one. Bridges were really the other thing. And like I said, you know, I acknowledge landslides, but I just haven't found a way to really deal with them and beat the wave. I just think that, like in Wheeler, there's so many roads that reach high ground. Maybe some of them won't be available, but there'll be lots of other ones. And what I would do with Beat the Wave would not be very illuminating. Yeah.
What would happen to neighborhoods that have water towers?
That's another open question. You know, it's likely. I mean, if they're, you know, if the water towers are, you know, unlikely to withstand the shaking, that they will, you know, leak or shift off their foundation. And I mean, whether or not it would be some sort of catastrophic failure, you'd have to do a site-specific evaluation of that structure. But there are some possibilities of what could happen. I don't want to say, you know, but that is something to consider. That's like a, you know, but again, for what I'm doing, that's not really something I would feel, I wouldn't be able to account for that and Beat the Wave, but it's certainly something that people in that neighborhood should think about. Yeah.
Well, and also, I mean, that it's up high.
Sure.
And so it might otherwise be a place where people would want to go. And if there's a water tower that's going to fall down and inundate the hill, then probably that's not where you want it.
Maybe, but again, so say it falls down during the earthquake shaking and, you know, there's an outpouring of water. You either react accordingly and go another way, or, you know, it's done and the water's on the ground and then you squish your way up the hill or something. I mean, you know, it's not going to be pretty no matter what. Okay, so that's really all I thought about with bridges, but I'm actually quite optimistic that removing the bridges is not going to actually change the results that much, like in Rockaway Beach, where it was so dramatically different between the two. In a situation like this, where there's high ground immediately south of the bridge by Wheeler and immediately north at Nehalem, it's going to look the same for everybody in Nehalem and Wheeler, whether or not those bridges are available, because their high ground isn't dependent upon them.
So just for our local knowledge, the Nehalem Bridge that goes over the river, is that earthquake?
No.
So it's going to go.
That's a new bridge.
Is it?
those of us who looked
Oh.
101 bridge between Wheeler and Hale, that's a new bridge.
So when was it constructed?
Yeah.
Well, within the last 30 years, because I lived in Wheeler.
Yeah, so anything pre-1990s,
Yeah.
and it's probably not, has not been designed to the magnitude 9 type scenario.
And I referred to an ODOT database
So again, we refer
Yeah.
to ODOT on questions like this.
Yeah.
Because they have been evaluating all these different bridges.
We live on University Avenue, which is on the ridge above a wetland, which isn't too wet right now. But anyway, when the wave comes up into that, because it's fairly, it's a valley type situation, but it's still fairly narrow in there. That's why I asked how many waves would be coming in. Right now, we're not considered in the inundation zone, but if these waves keep coming in for over a period of 16 hours, each time they come in, they're going to be undercutting a ridge like that, I would imagine. So basically, where we were safe before, it'll probably, right?
That's a great question. And our tsunami inundation modeling, like what was done before, assumes the landscape is made of concrete, right? It does not account for erosion, sediment transport. This is something that we're talking about. We're thinking about how that might change the look of inundation, especially through the course of it, as the first wave recedes and the second wave comes in, it's going to start to potentially saw at some of the weaker materials. But that was not accounted for, and so that is something that if you're really concerned about, you could talk to a, geotechnical engineer about it. But, you'd have to, or a geologist, to really consider how close to an edge you are and how realistic it are that the scour would truly compromise your structure.
To just have water scouring it, but you're going to end up bringing big trees and houses and everything else. Debris comes with it, so, and back out again.
Yeah.
Yeah, I'm thinking.
Yeah.
Are you looking for comments about your assumptions about those bridges?
Sure, yeah.
Because the McDonald Bridge on the east side of that,
yeah,
there's an island and there's a number of homes along the river. If that bridge is gone, those people are totally isolated.
I'm really glad you pointed that out. So there's not only are there houses I saw, I don't know this area, but I could just see in the imagery that there's houses east of on McDonald Road, east of the North Fork there, and there's also people that live on the south side of the main stem there, and so that bridge is theoretically, or not theoretically, that bridge is quite important to get them to high ground very fast.
They will not be able to go east from them. They're going to have to come up to us where the A is by McDonald Bridge. And they're just right across the road.
Yeah.
If that bridge goes, those people are going to drown. That's a reality.
Well, I'm hoping that they have boats that they can get into. I'm not even kidding. Like places like that. I mean, even without it being like, if you aren't able to use the bridge and bop right across to where there's high ground really nearby on the north bank there, that's quite a long ways to get back to high ground anyway. It's a mile. But this is all like really difficult terrain after the earthquake. It could be difficult. So yeah, so that's something that I would likely point out. And I think the Beat the Wave results, when I cut that bridge, if I let it in, they're going to have a walk, and when I cut it out, it's going to look really different. And so that's just, that's as far as I would take it, but it will be pointed out that this is something that could be, thought about more, maybe,
And again, this sort of information can actually be used to reinforce the point that maybe, at a minimum right now, you should at least have a boat handy.
Right.
So that's a viable option.
And a lot of those people do.
Right, and that's what we figured.
Yeah.
So then the other piece of this is then that's information, it highlights the fact that this bridge is pretty important for this area. And so this is information that again can be used by the community, the county, the state to then make the case, well, maybe we need to put some money investment into this particular bridge and reinforce it. That's where this information can actually help sort of drive that decision-making process.
Yeah.
Thank you.
You mentioned earlier that you wanted local input.
Yeah.
How do we facilitate that? How do we get that?
So, yeah, so I don't have maps to draw on today, but so you guys can email me if you have any additional comments you want to let me know that you don't tell me now.
I'll just give you a simple.
Yeah.
So can I make a suggestion?
Manzanita and First Street.
Okay.
Just remember those two things. Go take a look at it.
Okay.
So one suggestion I would make is that if you do have comments, I would suggest maybe sending them back to Linda.
Oh, sure. Yeah, that works
and,
too.
And then Linda can get those to us. That would be a very simple mechanism.
And I know there, particularly in Neocani, there are some trails that aren't on the map that have been upgraded by the county that we want to make sure they knew about. So if there's anything that you know about that's upgraded and
Yeah.
that you use, please let me know and I'll make sure that you guys know it.
I don't have super zoomed in on Manzanita itself, but I do have a close-up of in one area. I just wanted to show you an example of where we've actually gone ahead and looked at aerial imagery and the LiDAR data, and in speaking with EVC and Parks a month ago, already have put some hypothetical things in the road and trail network that we're preparing to consider kind of in and out. So this is the area that we've been talking about. The state park is where we have all these visitors that don't know where they are, and there's not a lot of high ground. So even if you do know where you're going, it's going to be a challenge to get there. So this is an area that we've really been focusing our energy on. And so these are the campground loops right here. And the boat launch is at the very bottom of the screen. The airport right here, and Horizon Drive, which is like the entrance to the park right there. So high ground in green, there is this ridge that comes down and is high ground, but there is currently no access to that piece of high ground. So right now, there's this little island of high ground, Necarney Hill, and the parks is using this. They're clearing it, and it's their plan to go up there. And I believe that they instruct visitors to the campground to go up there. But otherwise, besides Necarney Hill, it's the transfer station, which is like from the day use parking lot at the south end of the state park, it's like 2 miles to the transfer station. So Necarney Hill becomes very important. And it is, so again, XXL has a lot of conservatisms built in, and it looks like a small little island of high ground, but it's quite important. And so again, it becomes something where, I could do a scenario where I make everybody go to the transfer station, and then when people are allowed to go to Necarney Hill, and it'll show what an improvement it makes. And much like in Newport, where Safe Haven Hill was a very similar situation where it's this little, I call them islands of high ground, but it hits a really important population of people, and it's their only option. And so the city felt that was important, and they invested money into improving it, signing it, putting a cache up there, making it a place that people felt more comfortable evacuating to. So we also talked about adding some hypothetical trails from existing paved trails in the state park to reach that ridge of high dune to the east. Because if you're down at the boat launch, even Necarney Hill is really far away, but this is closer. And so, it's not actually that, it's not that big of a lift to build some new trail and sign it, as opposed to like building a vertical evacuation structure for millions of dollars.
One of the things that's been really helpful is that the state park is really working closely with you guys and with us.
Yeah.
And so you're going to see new signage out in that area, you're going to see new trails. The other thing that the park is doing, which I think is incredible, they are donating a container, a 40-foot container, that will be up at Manzanita Transfer Station, which will allow us to put supplies for the neighborhood that's in that area, but also for the park, the people that are in the park, which will have very, very few supplies.
Well, why don't they put a trail across the airport, right street of
That's what they're thinking about. Yeah, and that's exactly what they're looking into.
And it looks like they could travel up to the transfer station on higher ground.
Yeah, so I don't have that one drawn in yet, like right across, but those are the kind of things that, I know it's probably hard to see, but the dashed lines that are blue are the hypothetical ones that we've put in. And so little things like, it's probably a park service road that connects the camp loops up to, a main street in town that on foot you could walk, even if you couldn't drive your car there. That's not the point of this map, So, and even like over in Nehalem, actually, I believe this is Fern Street maybe. And like the road technically ends there, but in the imagery you can see that you could walk just a little bit further and reach high ground. So, I wanted to acknowledge that, because in reality that's what you would do. You wouldn't like have to walk around and go back up another street. So again, actually emailing Linda is probably the most efficient way, since you guys all know how to get in touch with Linda. And so if you have any additional thoughts or concerns, I don't have a close-up photo of Manzanita, but generally speaking, the road network in Manzanita is pretty dense, and a lot of roads intersect with high ground. And we did identify a few, paths that you can see in the imagery that connect roads that aren't drivable passageways and that sort of thing.
Okay, a couple more questions, and then we'll close.
Are all of these slides on your website?
No.
However,
but we.
So Gary McDaniels is our videographer.
Oh yeah, this video.
Wonderful job. And what Gary has done, and if you haven't seen them, his videos are absolutely incredible. They are on our website, and he will incorporate these slides in the video.
Yeah.
So that you'll be able to see the presentation, response to the questions, and the slides will be there. So that should be some good information.
Yeah.
Any other questions? Oh, Linda.
Oh,
if you were in a car during this, you were driving somewhere not too far from our town, is it best to stay in the car if there are electric wires nearby? Is there a bridge nearby? Give us a scenario of what to do in a car.
I believe the advice is to stay in the car until the earthquake stops shaking, unless there's some immediate situation that merits getting out for.
Wires that might fall in your car or something.
I think I'd rather be in my car for that. My plan is to stay in my car if I'm in my car. That seems like a nice safe space. There's steel over my head. I don't know.
If you're in your car and a line comes down on it, assume the line is hot. Don't step out of your car when it's over.
Right.
Jump out of your car
Right.
so there's no contact.
Right.
So Laura and John, this has been very informative. Thank you so much. We're very excited about this.